The first time we did the podcast, Brian essentially said, if you don't get a haircut, I'm not going to do this podcast with you.
I said it in a really harsh way. I meant it in a good heart. I want you to look good on the camera.
Essentially saying that I was ugly.
You're toxic, Brian.
This is the second episode of the Chainless podcast. And the idea is to go deep into the new paradigm of dApp development that is stripping away the idea of the blockchain and using proofs that are off-chain to verify transactions. Today we have Saul with us from Livy.
This is Brian from Polygon Labs. And today we're really excited to have Livy, who is building this thing called the provenance layer, which is essentially a decentralized TEE proving service where if you have any computation, if you can wrap it into some sort of a package, in this case will be container, you throw it to the decentralized TEE layer, they generate a TEE execution with a signature and provide it back to you. So that now you're equipped, you're returned with a computation result with a signature that says the computation was done correctly. Without further ado, I would like to introduce Saul, whom I actually met. We first met in a hacker house in Succinct Lab. Succinct Lab hosted a hacker house. And then I went there to check out because I'm super interested in their project. And there was a really cool dude who was right there. I just felt like, man, he has an aura. I have to go talk to him. And the more I talked to him, the more I realized, are you that Saul that I know of? And then he's like, hey, are you that Brian that I know of? So we pretty much knew each other before. They were building on top of Polygon layer. So that started the friendship. And eventually we also built a hackathon project on Succinct called ZK Hyperliquid. And eventually it led to a lot of different ventures on each of our own. And now he's the founder of Livy. And I am super excited to have him on this podcast and to share with us about himself, what he's building. And we have a couple of questions about some of these amazing stuff that he's building. I'll give it to you, Saul.
Thank you so much for interaction. I'm 23 years old, so I'm a kid here, basically working in crypto since probably the last 5 years, basically a software engineer, a computer science dropout, TLDR, first year of computer science. I was in this hackathon project with a couple of folks from university. We passed all the challenges that we have. We went to the final out of 500 students throughout the country, 80 plus universities. And we basically got finalists and basically got the top 3 out of Spain, which basically got me into my first full-time position. I dropped out of university first year. 2 years later, I started doing product. I started doing things on my own. So I quit the company and basically started working product, front-end, consulting stuff, when it comes to software engineer, product design, all of that. After that, super interested in the blockchain space. So I started going to the first hackathons. Last year in Brussels, we built the first concept with Polygon. Basically, we built this wallet with QR codes that also use the Polygon ACK layer. We were the first project to use the Polygon ACK layer in project. I was super interested in CK VMs at the time, what's CK, what was all of this blockchain stuff. So I basically got super into CK, trying to understand how this move math complexity works, and basically super interested. My last position was at CK Email. I was doing DevRel with them. And then basically January was my last month with them. And February, I built this initial concept that basically was like an image editor that used CK, in this case, to sync the CK VM to generate proofs of image transformations. We found problems with that, and that's why we built Livy. So yeah, that's pretty much my interaction.
Can you describe to the audience, what is it that you're trying to solve?
Yeah, so why I came up with this concept of basically using TEEs in order to create verifiable applications is with CK. Now, we should have solved the problem of complexity on how to build CK applications. Initially, you have circuits that you need to write, basically defining all the constraints, which is very complex. A couple of cryptographers that understood everything could basically develop CK apps. With CK VMs, we probably have solved that problem. Now we can just use Rust and it's going to work and generate a proof. So complexity when it comes to development has been solved. But again, you have a DSL. You need to learn Rust in order to build apps. Most of the time, you have other compatible programming languages as well. But usually it's mainly Rust, which is a problem for most folks. So that was one of the initial problems that we have. And the second problem that we identified basically was like performance. If you want to have like full security, CK is great. You're going to have that fully guarantee with proofs basically, which is great. But if you really need to have low latencies and performance for large computation, training AI models, for example, you basically can't do that with CK right now. It's basically too expensive and too slow to do that. So how can we bring like the same guarantees of security, verifiability, but without having these issues? So with TEEs, we can execute any programming language as well. We can execute any computation. We don't have pretty much any overhead. And basically, we have the attestation at the end of every single execution, which is one of the best properties of TEEs, that the finality is instant. Once you execute something, you have the attestation and you don't have to wait for the proof to generate.
I just want to clarify firstly, DSL, it's a custom language that a company develops for just their product, right? Is that what you're referring to?
It could be, for example, Solidity or for like smart contracts or Viper.
So you're saying that generally there's two problems with the ZK ecosystem. One is that it's very difficult to build on for a developer. You'd have to learn these new languages or you have to use low-level languages, and the process is complex. The other one is there is a limit to the type of computation that can be done in a ZK VM, even though it's more generalized. There's just so much more that goes into producing these computations. As a result, you're saying that TEE is a solution to do many of the things to have similar security guarantees, but in a much more efficient and easy to build environment. Would that be accurate?
So with CK, you can do a lot of computations that were impossible like a couple of years ago. But again, if you really want to run like extremely heavy compute or extremely low latency computations, you probably can do that with CK unless you're using like huge machines like do that, which comes to the second problem, which is pricing, basically.
A question that I have is maybe a little bit of context for everyone. TEE is a trusted execution environment.
So basically, a trusted execution environment is an environment that is trusted. So the idea is that there are like devices, which can be graphic cards with NVIDIA, CPUs with both Intel and AMD. Then basically, it's just a normal CPU that has like an extra hardware that allows to basically verify the integrity of the memory, the integrity of the boot. So you have guaranteed or like an enclave that the executions you're doing and performing basically on that CPU or GPU, it's going to be secure. And every time you make an execution, you have an attestation that proves the integrity of the memory, the integrity of the execution, and that provides a trust layer on top of like normal compute that you would never have if you just run a normal CPU and basically you just execute some. So just to summarize, like the trusted execution environment is this extra piece of hardware that allows you to verify execution.
So it has to be built on a special piece of hardware. It's not something that can be purely an emulation.
You can emulate that, but again, like the security comes from the hardware itself. So you can create a similar signature every time you make execution with software. But again, you are not going to have the security warranty that software has been run correctly. And that's something that the TE provides for you.
For the noobs out there, like myself, where do you get these like TEs? Is it you go to Walmart, you just go to the salesperson and be like, hey man, I want a TE. Show me your TEs. Yeah, like how does it work?
So essentially, it's just a computer AWS provides. Azure, there's other providers like Web3, for example, Fallout. Or you can directly go to like this super old enterprise company. Hey, I need a TEE with like 100 cores, 2 terabytes memory. And like they're going to give you like a rack that you just literally need to plug in. And then you have to configure, boot, and all of that to create virtual machines and basically create like a cloud itself. So it's a normal computer at the end. The only thing that you have to think about it is that obviously it's going to be like a huge computer, which is usually for enterprise service, that server, that basically that's the reason why you don't see a TE Walmart. So it's sort of niche, but you have like different providers for both graphic card like NVIDIA and then CPUs. It's both AMD, Intel, and you also have ARM with their Trust Zone, which is also like another trusted execution environment for smaller devices.
Your iPhone, that fingerprint thing is that ARM's like Trust Zone or is that their own thing? Is that something that you can program into too?
In the case of phones, you have the TE, which is basically for storing only. You don't have the execution of anything in that one. You can basically store anything and it's going to be secure. So like your signatures of your face, it's going to be secure inside that TEE. I don't know what's the name of the Apple one, but it's not programmable, which is like the main difference in between, for example, the Intel TDX with the Apple one in their devices, which is like fully programmable. You can execute anything that a normal C would do. But in the case of Apple, it's basically for storing information.
Jump in a little bit. So you've been talking a lot about some of the benefits of TEE, and we covered the introductions. I would also wonder what are some of the limitations in terms of, say, hey, this is a trusted execution environment, but assume it's going to use memories, it's going to use storage, and those data that you store also has to be in an encrypted form. So what are some of the limitations of TEE, and how do you think are some of the solvable ways around it?
Yeah. Like the limit with T is basically like how we can be the enclave that it's basically secured. You cannot encrypt or like basically sign on the hardware directly. For example, the data on the hard drives that cannot be signed directly because you're basically signing memory and not all of it sometimes. So it's basically like that limit on like how big can be the program. But usually this space is going to be big enough to run any sort of computation. But if you want, for example, to run a database inside like TEEs, that's going to be, for example, a limit, especially once you scale, because you're basically not going to be capable of storing terabytes within the enclave, which is obviously a limit. But for generic computations, like normal program, which is going to take kilobytes in the worst case, megabytes, and then the state execution can be stateless, and then basically you do the state transition. And again, if you want to have like persistency again, you still manage to have some space that allows you to use the TEE in a secure way. So if you want to have data intensive applications, probably that's not going to be like the great scenario for having storage or stuff like that verified within like the TEE. But when it comes to execution, it's great.
I see. And yeah, I think that makes a lot of sense. And for general computation that doesn't require that much data, then running in TEE would just be almost the same performance as running on the normal like CPU or GPU environment. But when it comes to you have a lot of data access, IO between the memory and also the storage with the CPU context, even in the CPU context, there's already a lot of overhead. But now you're dealing with an encrypted IO between memory and also with the storage. So that's going to be additional overhead. So I guess it would just be a limitation to what kind of application that you can design for that. Majority, you're saying it should be able to host it, but you should have that limitation in mind when you're designing your applications. The second question I actually have is about like the hardware signature security itself, because there's a lot of debates in the blockchain space saying, hey, TEE is cool, but it's like that there could be side channels, there could be a lot of ways to hack it. And that's why people are looking into ways to decentralize it so that these TEE environments are being randomly selected so that you can just mitigate that, whatever side channel attacks and stuff. I wonder what's your thoughts on this and what is like Livy's solutions around it.
So yeah, side channel attacks is one of those problems that TEs potentially could have. The way we try to mitigate that idea is basically through the provenance layer. Like the execution can basically have these side channel attacks, but if you verify the attestation at a different node or like a different TE than the one you're executing the code, you sort of mitigate these issues. But again, it's not going to be fully perfect like CK, but basically we're designing these sort of mechanisms to mitigate these issues that TEs potentially could have.
In a security spectrum, we could say ZK is probably like the maximum security, or let's say even Ethereum is the maximum security because it just has so many nodes out there. That's why we entrust Ethereum as like a lot of the layer twos, they entrust Ethereum as a settlement layer. They hack their securities onto Ethereum. So if Ethereum is the maximum security, ZK is similar to that level. And there comes the decentralized TEE. And then so consensus, ZK, they're all there. Consensus varies depending on how many nodes you have in the network. But things like Ethereum and Bitcoin is on the furthest left. And then on the furthest right will be a centralized server with no ZK, with no TEE. You just say whatever you want. That's the Web 2 style. And decentralized TEE is way closer towards the ZK side. But if it's just TEE, maybe the security stands in the middle of the spectrum. And if you go down a little bit, it's just fewer nodes consensus, like 6 nodes consensus. Some layer ones are doing that. So yeah.
Yeah. One of the notes I want to have is like you mentioned, like CK is less secure than Ethereum. I would argue that CK is the most secure thing. Basically, you're just relying on pure math. And then maybe ETH is great for dynamic security. And that's why we trust that. But I would argue that Snarks or like Strunks, whatever proven system you use is way more secure than Ethereum itself. Because if you break that, like basically you don't have anything else.
Yeah.
But I agree that basically DEEs could be in the middle.
I would say Ethereum level consensus, it's like on the same level, similar level of trust. Or actually, you're right. ZK is way more, but it's just like Ethereum is really secure. I guess that's the point that I'm trying to make. But yeah, ZK is like maths because it's absolute. As long as there's no bug in the circuit, then it should be right. It's like 100% correct.
Yeah, I like that's another topic.
Yeah, but then you have, if you want that 100% security, then you need to go through the formal verification.
There's that triangle, right? If you want to have absolute security with math, then you get super complex, difficult to verify, and hard to understand stuff. And then maybe on the Ethereum side, it's not as absolute, but you have these like economic guarantees. You have some other factors that kind of make up where it's easier to understand.
There's like additional axes too. What we're discussing is like a horizontal axis on the security side. And on a vertical axis is probably, I don't know, scalability or maybe like cost or performance, etc. I feel like all of those could be its own axis itself to like distinguish Ethereum and ZK. And the reason why I use the term Ethereum specifically is because there's no other blockchain, programmable blockchain that can achieve Ethereum level security in the world right now. So that's like the golden standard.
We're just trying to contribute to the pump of the ETH price. Let's take a
Big pause.